So then here is our safe and sustainable innovation approach, which you've just seen. Now we translate this into a decision support system, which is modular by nature. So each of these phases now has one or two modules. The first phase, the ideation business phase, has two modules, the AMEA and the WASP. And this is very, very basic questions you have to decide. Does it consist of particles? Is it nano-enabled? Is it advanced? Then for the WASP, we offer 12 questions you can answer typically quite easily on exposure, hazard, and sustainability. And then you will receive warning flags and design advice, screening priorities. And then in the lab phase is the first time we actually collect data ourselves with our NAMs. And this will then represented in this color-coded response and preference matrix, where we have the advanced materials, the conventional material, and reference materials. So always we keep reference materials for all of our materials so that we have a framework of toxicity. And in the pilot phase, then this will be much more complex. Many more levels are involved, and you can make an overall view of what you have, make a decision based on that information. Then this is also aligned with an effort towards an early warning system within the risk and governance process for advanced materials. Of course, this is a concern. And for that, you have a very similar kind of problem. You start with a lot of materials. You want to condense it down to the most relevant ones. So you may have a pre-screening tool, which we don't have, but we have this kind of harmless early warning tool, which is where you have to answer basic questions and do some screening efforts to find out which materials are of most concern, which should be prioritized in terms of attention from the regulatory side. And then you might also want to define some follow-up actions for that. And of course, you could have more detailed assessment. So this is essentially in a nutshell what the early warning system does. It is very well aligned with the decision support system I've just showed you earlier. So here is the concerns, exposure, hazard, sustainability. That is exactly matched here. So we try to align this as best as possible with the decision support system, which guides the innovators and inventors. And then this should also then facilitate the communication between regulatory and innovators, because supposedly they have the same structure of thinking by the time they talk to each other. Very heavily emphasized in this project is data generation and model generation. So we start with materials, which we have selected, then we apply models and cell types. It can be cell-free models, all kinds of models, assays to characterize the material. Also omics is involved for genotypic anchoring. Then we have AOP assessment. I will get to that later on. We then eventually do in vitro, in vivo extrapolation for predictive modeling, so that you translate the NAM information into in vivo relevant predictions. And we use integrated approaches to testing and assessment and other tools. And as I mentioned, we develop NAMs, quite a few. I'll get to that in just a second. And of course, we use existing data, but we also generate a lot of new data. And then, of course, the training of the predictive models typically relates to you have training data and then validation data. So very quickly on the NAM side, so we have all in all 37 NAMs, which we followed through, modified or used throughout. Here are the key parameters which we are addressing with them, just to say a few. So it's exposure, it's dosimetric tissue delivered dose, surface activity, release of toxic ions, then inflammation, genotoxicity, and so forth. And for that, for each of those, we have then defined at least one NAM, and they're color-coded according to the phases of product development. So lab phase, the early phase is blue. So in the early phase, we use BET surface area as the key dose metric. We use electron microscopy for phys-chem analysis. We have some very simple ROS assays like FRAS, EPR, DCFH. And we look at in chemical solubility in relevant media, especially the phagolysosome or just aquatic media. And then in the pilot phase, of course, you have more advanced NAMs, in silico exposure modeling, for example, or cellular oxidative stress measurements via protein carboxylation, or advanced in vitro cell-based technologies, high throughput assays. I'll get to that in a second. We use benchmark dosing, clustering-based grouping, in silico predictive hazard modeling, and on the ecotox level, we also have in vitro ecotox included. And all of this is guided, how to integrate now these NAMs for the specific materials. This is then guided by the integrated approach to testing and assessment, where we heavily rely on the Gracious project, and we refined and expanded their approach. Another important part of descriptors and NAMs is the in silico descriptors. There we have more than 1,000 molecular descriptors per material. Much of it is based on quantum mechanics, which allows you to derive, based on the electronic properties, some relevant descriptors like ionization potential, electron affinity, energy band gap, electronegativity, and so on. Then quickly on high throughput screening, in vitro assay, where we do pipetting not manually, but with robotics to make this more efficient. It's on a 384 well base, so really high throughput. For each of the materials, we test 5 different endpoints on 4 human cell types, at 3 different time points, and we have a full dose response curve for each of that. And then, of course, there's the analysis of the different levels of toxicity in terms of lowest observed adverse effect level, for example, And all of this information is then condensed into a TOX5 score, which is a hazard score based on all of this information to the left. And this allows hazard ranking, which I'll show in a second. So 25,000 data points per material is what we're looking at here in this high throughput screen. Then you can rank with this information. Now you can rank the materials. We have, as I mentioned, reference materials and case study materials. And red, of course, is highly toxic and green is low toxic. So you'll see that you have a full range of red and green. And within this framework, then you can discuss where your material of interest ranks. Now, the concept of adverse outcome pathways you're probably familiar with, where you have key events, molecular initiating events, which lead to some adverse outcome pathway. And these events can then be described. We take the approach of, this is a more complex representation. I'll skip over this in the interest of time. So we address this in terms of transcriptomics. For now, we have the data, transcriptomics data, but we haven't processed it yet. So here we present an example from the literature with MinuSeal quartz on A509 cells. And we were able, with the methodology, which is predictive toxicogenomic space analysis, we were able to identify all 28 lung AOPs, which can be described with GO terms. And for this material, we identified inflammation as one of the adverse outcome pathways. Is in fact 11 of them. For cancer, we found 7 AOPs, and for fibrosis, we find 2 relevant AOPs. So this is all of the known adverse outcomes pathways for MinuSeal. Proteomics, in addition to that, not just transcriptomics, but proteomics also is very successful in describing the type of toxicity. Here we have a paper published in Advanced Science describes the pathogenic carbon nanotubes and identifies a clear transcript and proteomic fingerprint. This is a meta-analysis of existing data, so not our data. Then on that level, on the proteomics level, we also have identified that when you do cell culture experiments, the type of proteins you use, the exact culture conditions play a role in outcomes. So harmonization of protocols is essential. And to that effect, there was also efforts to identify better protocols for proteomics. Yeah, then ecotoxicology is also a key component of our project, where we focused on persistency of materials in water, so dissolution assays. The second level interest was on the point of entry, so the other was bioaccumulation of the material in different species. We used Daphne, algae, and fish. And that was integrated then again into the harmless decision support system. We had several initiatives trying to support OECD efforts, for example, on the guideline level, where new guidelines for, in this context, fish cell lines are derived or at least refined for nanomaterials. Here, the cell type is a rainbow trout and gill cell type. And very interesting to us when we saw this is when you look at the ecotox and the human tox in vitro data. Yeah, this is the high throughput data, which I've shown you earlier. This is now the ecotox data with the fish gill cell line. You see that the color coding is very similar. So the perovskites are very toxic. Also, copper oxide is toxic. And then many of the other material oxides are not so toxic. And you see a large similarity between the fish and the human in vitro cell type. I think that's quite interesting. Shows how omnipresent toxicity is in many ways in different species. Now, quickly, what do we do with this? So ultimately, we have a lot of data on the NAM level, but of course, we want to relate it to the outcome on the in vivo level. So we have mouse data for pulmonary application and rat inhalation data for pulmonary application, and the rainbow trout ecotox data. So you take, for example, lung liver genotoxicity in vivo, and you try to model it with the NAM information to identify, for example, the lowest observed adverse effect level for each of the materials. And then you can compare what you measure versus what you predicted for the different types of endpoints you have. And for example, the DNA damage in bronchoalveolar lavage in lungs of mice, you find that the NAM prediction model, which we have here, gives you more than 90% predictive capacity and validity. And here's the relevant descriptors: aspect ratio, BAT surface area, and nanodimension, and ROS. So Agnieszka has done a lot of models, more than 100 in silico models with different data types. I don't want to go into too much detail, but maybe the key outcome from that is what are the most predictive descriptors? Phys-chem properties, of course, like aspect ratio for HARN or BET surface area, as well as ROS production, and to some degree also dissolution in phagolysosomal media. Electronic properties also play a role, so band gap energy, valence band, conduction band, and electronegativity. So eNanoMapper is the database, but not only. Of course, it stores data, and it also makes it fair if you allow it to be distributed by a Creative Commons license. There was a lot of SOP and protocol harmonization, quality assurance going into entering the data into the eNanoMapper framework. There was a lot of work on a template designer to put the data entry in a more kind of easy to handle stage. Then there's also efforts on data visualization and processing. In the ToxFairy module, for example, there is now data mining tools where you can use AI-based natural text language to retrieve information from the universe, from the internet. And then, of course, this will be integrated also in our DSS system. And I think I have to hurry up, but very quickly. So I think, I hope I could convince you that we have made important contributions to the test and method harmonization. We have important contributions to the integrated approach to testing and assessment, as well to the AOP structure. And this can safely be said is the largest data set on industrial relevant advanced materials, especially with focus on harm and mixtures of metal oxides, which are valuable for several follow-up studies and, of course, our own activities. In vivo and EOP anchorage was a critical point, and the predictive modeling, as I showed you. And then finally, of course, the decision support system is a modular approach. We have shown the early warning system for regulatory purposes is harmonized in terms of structure with the SSBD system. And ultimately, this is now available also as an easy-to-use online decision support system tool hosted by TNO. And here is the information for access. Yeah, with this, I would invite Susan to present the next talk.
Please, Blanca.
Yes, so thank you very much, Susan. I'm going to start introducing the safe, sustainable innovation approach from HARMLESS, and then how we develop our framework. And from there, Susan will into the decision support system. So first, I just wanted to have a quick overview between the difference between the safe innovation approach, or SSIA, and the SSBD, because I see many different people here with different backgrounds. So for some of you, this is already very well known. Others may not be aware of it. So basically, initially, the safe innovation approach was developed in the project NanoRec2, mainly by the leadership of RIVM. And the idea was to keep an eye on emerging risk materials. And in that case, we were working a lot with nanomaterials. So the safe innovation approach was subsequently updated with the sustainability part, because chemical safety is also part of the UN sustainability goals. So it was also introduced and became the SSIA, the SSIA approach. As you can see here, we have two different, mainly three different blocks. As you can see at the bottom of the slide, we have a part for innovators, which is what we call safe and sustainable by design. Here we try to help innovators to reduce uncertainties regarding the development of their materials or products, to address what I just mentioned, the emerging risk materials. On the other hand, we also need to take care of regulators, because innovations happen very fast, and regulators sometimes struggle keeping pace with innovations. Regulation have to be updated, and then so the regulatory preparedness part of the SSIA was also developed having regulators in mind. And because we also wanted to foster a dialogue, then we were also creating this other part of the SSIA, which is called the trusted environment, which seeks to encourage dialogue between innovators and regulators. So initially this came up under the NanoRec2 project, which was working on nanomaterials, but it was actually proposed by the NanoRec2 coordinator in ERIS, together with RIVM, JRC, and VIAC, to have a project at the OECD level. So the OECD will also support the development of SSIA. So just to also let you know that the HARMLESS took care of both branches, the innovators with our framework and decision support system, but also the regulators, where we developed the early warning system, and you will hear about this later today. Can have the next one. So if we now focus on the SSBD approach developed for innovators in HARMLESS, to tell you that this builds on previous initiatives, mainly NanoRec2, Calibrate, and Gracious. It also builds on the three main pillars, which are safer materials and products, safer production processes, and safer use and end of life. We follow a lean stage gate model. We all obviously take into account safety and sustainability, and we have also introduced, like Otmar just mentioned, design principles to help innovators implement our framework, but also tools, which also Otmar mentioned, to implement those design principles. Can I have the next one, Susan, please? So just to compare the full stage gate innovation model developed, well, this was published by Cooper, and you can see here 5 innovation stages which encompass scoping, business case, development, testing, and launch. In Harmless, we have gone through the lean approach, because the full approach is lengthy and high risk for companies because they may bet for a product, and after this long development process, the product may fail. So companies follow linear approaches where different stages are merged or they run in parallel. In the case of Harmless, we have 3 stages, which were the scope and business case. We have the lab phase and the pilot. Can I have the next one? And next. The Harmless framework also have some boundaries. Can you go back one, please, Susan? Yes, have some boundaries regarding safety and sustainability, regarding and also we all look into the cost effectiveness of our models as well. So we look at climate change, pollution prevention, resource use and circularity, and then overlapping with safety, we have environmental health and also human health as well. So these are the boundaries of the framework. Can I have the next one, please, Susan? Now, this was already presented by Otmar. So this is our framework in a nutshell. So in the 3 different stages, we look at the 4 blocks that you can see above. We look into intrinsic safety, human and environmental safety, environmental sustainability, and performance. But of course, the different stages have different scoping and also different information available to them. So in the first ideation and business case phase here, we don't have a material yet. But what we do have is a very clear functionality and a clear market as well. So what we could do at this stage is to do a scoping review on the individual components of our material to see if we can see any hotspots or highlights for harm. We could also perform a very early qualitative risk assessment, and we can also have a look at which sustainable development goals we want to address. And we know about the functionality of the conventional material, so we can, of course, we will aim to improve this functionality. So the ideation and business case phase is information gathering exercise on the available literature or our previous knowledge on the topic. Now, if we move to the lab phase, can I have the next one, please, Susan? Yeah, here we will have different versions, and the idea is to compare our different versions of our materials. Of course, we will also have material to perform experiments, but in Harmless, we have tried to reduce experiments to a minimum. I said before, we try to be cost effective, and we are using, like Otmar already mentioned, a lot of modeling tools and in silico tools. We can already also have a look at the performance of the different versions and choose our best bet for this. And can I have the next one, please, Susan? And now the pilot phase is mainly there to verify the data that we have collected in the lab phase. And here, of course, we have material to do more heavy testing, perhaps following OECD guidelines, and also to do some quantitative risk assessment based mainly on in vitro. Regarding sustainability, perhaps at this stage, we could already perform an LCA. And we can also try to fit the circularity indicators from the World Business Council of Sustainable Development. And of course, we will have the performance of our final product. Can I have the next one, please, Susan? And just to mention that we do have design principles addressing all the items I just mentioned in the previous slide. This is only an example of the design principles or guidelines we may have at the different stages from ideation to lab scale to pilot. For example, very early, we should look at legal restrictions or to check if any of our chemicals fall into a substance of very high concern. And of course, look into our previous knowledge regarding physical characteristics links to safety, for example, high aspect ratio nanomaterials, persistency, etc. So this was in a very fast overview our framework, and now I leave the floor to Susan. TNO has been basically developing the decision support system to realize the framework into our tool. Thank you.
Yeah, thank you, Blanca. Can you hear me? Yeah, good. So basically here, this slide is the transition. So we used the SSBD approach just explained by Blanca, and build it into a decision support system. And I'll tell you a little bit more about that. Our objective, first of all, was to support industrial designers in their development of advanced nanomaterials, so the complex HARNs and the multi-component nanomaterials. Throughout all innovation stages, as pointed out by Blanca, we have divided it in our project in 3 stages, but it's flexible, including all life cycle stages from the production up to end of life, and integrating all the knowledge and the models and the data into a user-friendly system. So that was our objective. And for this, we have built some new tools, and we have connected some existing knowledge and information and tooling into that. So this is a quick overview of the workflow through the decision support system. Starting with the ideation and business case phases, we have developed the AMEA tool and the WASP tool. And moving into the lab phase, we move into the ASDI tool, and then later the pilot phase, where we really try to give an overview of all the different SSBD aspects. And what else can I tell you? No, I will tell you a little bit more about each of these tools. So I will move on from now in the interest of time. Starting, of course, in the early stages with the AMEA, the Advanced Material Earliest Assessment tool. This is a tool that was previously developed in another project, and we further developed it within HARMLESS. It's been published on the right side of the slide. You see the publication by Wendell Wolleber and all. And here on the left side, you see the different parts of the tool. It's actually very simple. You answer 3 questions, and based on these 3 questions, you will get advice. And then you can specify your advice. So the 3 questions here is, does it contain or consist of particles? Is it nano-enabled? And is it advanced? And based on that, it comes into one of the categories. And that actually triggers, so you can then look into the innovation stage you're in. Here's the early innovation stage, and you'll get your design advice. So this is one part of it, but it moves on basically to even more specific advice. And here it's a little bit small, but just yeah, the coloring also gives an indication if it is tailored to your advanced part of your advanced nanomaterial, or if it's more triggered to your multiple component, for example. It gives you advice on how to move on. So basically, AMEA was and the AMEA advice and the design principles were also used in the next tool, which we built for this innovation stage, which is called the WASP. And the WASP tool is actually, it's warning flags, design advice, and screening priorities. So it's basically 12 questions on safety, the exposure part, the hazard part, and some questions on other sustainability aspects. Here is a screenshot of the first question. In total, there are 12. They're on this sheet. So some of them are connected to the hazard part, some to exposure, some to both of them, and some to the sustainability. Actually, the question 12 has a B, C, D with the different SDG or the different SDG targets that we selected in our projects as relevant for basically focused on environmental sustainability. So basically, if you fill in these 12 questions, you'll get warning flags and design advice. And here you see one question, and it's answered with yes, triggering a warning flag. So on the left side, you first get design advice. So what can you improve to not get the warning flag? And some assessment advice if you move on, which descriptors you can consider in our next tool. And this is actually done for all the 12 questions. You get advice on how to move on. So if you move on with the ASDI tool, the Alternative SSBD Design Inspector, then you'll go and start actually generating and looking for existing information on your material itself. First of all, you start with dividing your design space. So often you have more versions of the same materials, which are slightly different. So these are the advanced materials or your SSBD versions. And you also have some reference materials and some conventional materials for comparison here. So you will have descriptors to really tell them apart, see where they differ. And then based on your WASP outcome, there will also be some descriptors that are triggered by the warning flags, which you can also decide to select and collect data on for your SSBD versions and your reference and conventional materials. So if you fill in here, you can fill in the actual values, and that will trigger or result in the result page in having this sort of a heat map overview on how your materials perform against the benchmark, the reference material, and compared to each other. So the lines, here are a lot of lines indicated by the dimension. So we have, of course, the performance you can include, which is important in selecting which of the materials you want to move on with. The design space, but also here are the descriptors specifically for the safety, the human safety, environmental safety, and sustainability. So if you zoom in on these tiny little lines, you will have, the next slide. Oh, now I go too fast. So you can actually see for the individual descriptors how the different materials perform. So you have a more detailed view. You can even either click on it to get more information there, but that will go too far from now. Then the next stage, which we call the pilot phase. Here we try to give an overview of all the different SSBD aspects on how you are performing. So one of the things we can start with is the Licara 4.1. Some of you might have heard or worked with previous Licara versions. We have modified and improved the Licara tool so that it now includes the hazard banding and the exposure banding. So you don't have to go to another tool like Stoffer Manager, fill it in and come back to Licara with your hazard band or exposure band, because the questions here are included, so it will automatically generate the right hazard and exposure band. What we also did is change the visualization to actually make it for a purpose of our work to really get here a sort of a status wheel in which you can see on each of the dimensions how your material performs. So basically that you have a line which is actually a point estimate, and then the surrounding this line you have the uncertainty. And then, yeah, we have included, of course, human health, safety, environmental sustainability, and some social economics. Also in the pilot phase, through the decision support system, there are some other tools which you can, which are recommended and which you can use to even get a more quantitative estimate for some of these aspects, SSBD aspects. So, for example, you can use the tier 2 testing methods, for example, from the Gracious if you're testing nanomaterials, in vitro NAMs, but we've also had some added the quantitative predictive exposure and hazard models, which are under development and are developed within this project. So in the future, you would also like to add the feature that you can actually add your own segment to the status wheel, no matter which kind of NAM you have data from. So yeah, this is basically a quick overview of how we have done this. You say that how we translated the SSBD approach into the decision support system. But as Blanca already told, there's also the regulatory perspective, and we've also worked on that. So we have the early warning, and this early warning has been translated into the early warning system, which is also part of, or especially the simple version in the middle bottom, is actually really similar to the WASP that I just explained in the innovators part. So this means that it's very much aligned, and it will really facilitate the discussions between regulators and innovators. This is also part of the decision support system. This is a sheet, and I would like to refer you to the pitch later on the early warning system, on what it looks like. I have to move on. I see future perspective. So we are still working on the pilot phase, on the methods and the tools, and we have are in communication with OECD for our early warning system to see if we can connect it to early for ATMA, which is developed within OECD, within the Tier 1 assessment there. We're also can develop customized tools for industrial companies, and also extend our applicability domain, building non-particle specific, non-nano specific tools, for example, in Planets project. So thank you. This is it for now. If you want more information, please visit the website, the Diamonds platform website, where you can also register today, get a pre-launch demo version. And we also have some preprints for our publications on this approach and the decision support system here.
Thank you, Susan. Thank you, Blanca. So we do have time for a few questions now. If you want, share your thoughts, ideas, questions, either by raising your hand or by just putting a question mark and a question behind it in the chat. Of course, we will also then have the chance to personally interact with some of the key players in this consortium in just a few minutes. That's also a good way of asking questions and getting feedback. Okay, so apparently, at least I don't see a question either in the chat nor by a raised hand. Then I would proceed. There's in the little why not considering all of them planetary boundaries. That is challenging.
Maybe I can answer that. We would have liked, of course, to extend it. And now we have focused within the decision support system for now, especially in the ASDI, on environmental sustainability. I see Blanca raises hand. Do you want to interrupt, Blanca? Okay.
No, go. I will add something after
because
that.
This project, it started off as an SBD project, so only safety included. But things evolve and sustainability became more important. So we took it along, but we had to make choices. We couldn't do all. So we took the choice of taking the most logic first thing to include, which was environmental sustainability. So we haven't put a lot of social sustainability and other dimensions in there. Blanca, can you add to that?
Exactly. So when the projects were written, it was just safe by design, and SSIA with one S. When the projects were awarded, everything had moved on into sustainability. So we really put all our energy as far as possible. But if it had been planned from the beginning, maybe we have done some obvious things as well. Just wanted to add that on top of what Susan already said.
Does that answer your question sufficiently, Elise?
Yeah, thank you.
Right, then in the interest of time, I think we are right on time now when we move into the pitch presentation section. And so there you will see one presentation after the other. If you have the program, you can follow through with it. Otherwise, you just are surprised. And with this, I would invite the first presentation on high throughput screening from Roland.
Okay, thank you very much. We had an excellent introduction here by Otmar and of the data generation. You see the same slide again. I boxed here the particular part that I'll address. So this in itself is a sort of a mini IATA from the fact that we do phenotypic anchoring first with the high throughput and then move into the omics analysis and essentially translate via the gene ontology, as Otmar described, the omics finding into AOP assessments and anchoring into the AOP. And then these are then used into the IV-IVE discussion, further things in the project and the tools. And if I go to the next slide, then if you can take the next slide, Bea, here's a little bit of more detail that I can even talk a little bit more on when we have a chance afterwards. So you see on top the high throughput aspect where you go from multiple to multiple concentration assessment, and Otmar already presented this. Then you move on more selected materials and selected concentrations into omics analysis, and we use this tool that I'll explain for you, the predictive toxicity space tool, and analyze via omics cytotoxicity indications, which AOPs are really activated and so forth. And then this is also a means of grouping and ranking, as Otmar presented in the presentation. Essentially, the idea is to go fully high throughput from the traditional to the high throughput. Also here we have incredible cost saving now. We're down to about 25 euro per sample actually, and analyzing omics at high throughput. Thank you.
Hi everybody, I will continue among the omics, but precisely with Proteomics, and I will show you the work at the BFR. And we started the HARMLESS project with a very basic protocol, that is the LFQ. This is a label-free quantification when we want to quantify proteins using proteomics, and this we had running in the institute. But please go to the next slide. What we did during the project was to advance this protocol, meaning to incorporate another technique for quantitation that it's called tandem mass tag, or TMT, which is commercially available. The protocols are also available, but we could optimize it, meaning that we could lower the cost dramatically, and also the amount of material, of biological material that we needed. So this was done for cell culture, meaning we had this new protocol, but for cell culture. And please do the next slide. This protocol was published in Small Methods, but we continued the adaptation of it to incorporate another biological materials rather than cell pellets. For example, lung, liver, or valve. Yeah, please to the next slide. And with these protocols, we could measure, for example, in vivo settings, liver, lung, and valve, with some perovskites, for example, or advanced material. They were treated like this, and we could detect the proteomic changes at the tissue level or valve. But also in the in vitro settings, we tested nanofiber toxicity using our protocol. Yes, please to the next slide. And here it's a bit the summary of the publications that were originated. And if you want to know more, we can discuss in the breakout groups. Thank you.
Okay, hi everybody. Let's move to the predictive modeling. So to capture the diverse properties of harmless case study materials, such as topology, geometric properties, and electronic properties, a comprehensive set of over 1,000 in silico descriptors was calculated. Key predictive descriptors, including electron affinity, band gap energy, and electronegativity, were derived from quantum mechanical calculations to provide insight into the reactivity of these materials. Please, could you go to the next slide, please? More than 100 in silico models have been developed using both qualitative and quantitative approaches. These models include local models focused on specific material groups, for instance, perovskites, and global models with much broader applicability domains. Key predictive descriptors include physicochemical properties such as surface area and thrust productions, as well as electronic properties like band gap energy and electronegativity. Could you please go to the next slide? A variety of different NUMs were used to assess the hazards of nanomaterials and harmless case study materials. One example is the integration of QSAR predictions with data from in vivo studies to predict material-induced genotoxicity in bowel fluid, lung, liver, and neutrophil influx in mice. Could you go to the next slide, please? We successfully developed in silico models capable of predicting in vivo genotoxicity and inflammation across various exposure doses, durations, and broad applicability domain. The resulting QSAR models demonstrated strong predictive performance and fully complied with all OECD principles for QSAR model acceptance, as confirmed by internal and external validation. In addition to experimental conditions such as exposure dose and duration, other factors including aspect ratio, surface area, Ross generation, and metal ion release have been identified as key drivers of material-induced in vivo toxicity. In summary, one of the key takeaways from harmless predictive modeling is that while in silico descriptors are extremely useful for developing models to predict in chemical or in vitro data, they alone may not be sufficient for accurately predicting in vivo toxicological responses or developing in vitro to in vivo extrapolation models. Therefore, the integration of data from a comprehensive set of NUMs is essential. Thank you.
Yes, and I'm happy to take over. I'm Anders Baun from the Technical University of Denmark, and I'm presenting here for INEA and for BASF with the people you have on the slide. Can I have the next one? In Harmless, we have, for the environmental part, been looking at the three parameters, persistence, bioaccumulation, and toxicity, and try to link it to the safe and sustainable by design context. When we talk about a persistency evaluation, we have been focused on, does the material actually stay in the nano range? The reason why we are preoccupied with this is that it was only if the material stays there that we would expect novel properties and potential problems with the test systems, or to look for new effects for the organisms that we are testing. Here we have narrowed it down in the SSBD context to looking at dissolution and agglomeration dispersion stability, which we have documented a couple of papers, and I'll be happy to share more insights in the breakout session. We then moved on and say for many materials, it's actually bioaccumulation that ends up becoming a problem from the environmental point of view. And therefore, we looked at organisms in the lower end of the ecosystem, being Daphnia, algae, and finally moving up to fish, but in a structured way, trying to figure out how can we do this so we save money and in the same time can do it with limited amount of material, for example, and also get information for informing the decision support. All this is linked to the safe and sustainable by design approach, but not only for that, but also for the, I think on the next slide, there'll be a little red box appearing, or not. Yes, we need to do ecotoxicity testing before we do these kind of things, and therefore there's been also quite a lot of focus on test development in Harmless. So if you want to hear more, come to the breakout session.
Nina, are you ready?
Yes, do you hear me? Do you hear me?
Yes, we do.
Okay.
Yes.
Okay. Yeah, let's go to the next slide. I would like to present the current developments of the eNanoMapper. And for those who have been following and participating in the efforts of integrating nanosafety data, we now would like to go towards AI-ready data. We have a new web address, but not only. Of course, we continue to store and make the EU data fair with high degree of attention to all the characterization of material properties and assays with SOPs, links, and a lot of metadata. This is, of course, not easy. And for this, we have developed a range of tools. Some of you are familiar with Template Wizard, which was published last year. And now we have new tools to facilitate development of new templates, which is called Template Designer. It's completely free for everybody. And last but not least, we would like to to enable you to make the data fair yourselves, starting from the templates and generating a standalone self-contained interoperable format, which can contain a lot of different kinds of data in one file, and also is one of the files recommended by Research Data Alliance, namely Nexus format. We can store analytical results and dose response data. And of course, the reason of going into such change is to enable automatic processing of the data. Meanwhile, we have been trying to make use of the latest AI developments with extracting material information and building a database helping you to define or find whether you have advanced materials, and maybe helping to answer the questions presented before by DSS. There is also development to enable chatting with adverse outcome pathways wiki. This is an ongoing effort and is described in a GRC report, which will be public shortly. And last but not least, going beyond database means that we would like to enable modelers to automatically reuse the data which is gathered from in the database. And for these reasons, we have developed automatic workflow to verify and analyze, pre-process and analyze high throughput screening data. All this huge amount of high throughput data, which was presented by Professor Roland Grafström, and at the end derive toxicological profiles per material. This is also has been applied to ecotoxicity data. So please come to the breakout room. We'll be glad to discuss whether this direction is what you also dreaming about fair data and most importantly, reuse of the data.
Hello, everybody. It's my pleasure now to be really brief on the harmless early warning system for advanced materials. Please go to the next slide. And instead of speaking faster, I would like to advertise again the dedicated joint OECD workshop that we organized together with the Sunshine and the Sunrise project on April 1st. This is not a joke. So here you see again the harmless early warning system in a nutshell. We address the pre-assessment phase of the risk governance process. Please go directly to the next slide, as Otmar has already explained that one. So here you see a simplified version of the harmless early warning system. It consists of two tiers. It can be preceded by foresight or horizon scanning tools if that is necessary or wanted. So we address the pre-assessment phase. We start with the tier 0 where you gather basic information. The underlying tool is the AMEA tool that is integrated in the decision support system, as you have heard. So it's 4 simple questions. The 4th one has not been introduced before. That is the category question, and we need that for the sustainability assessment. So we have to compare the advanced material towards a conventional material to understand if it's more sustainable. And also we would need the category to choose if the norm is actually adequate for the chosen category. The screening is existing in 2 versions. So we have the simplified version that has been presented by Blanca and Susan already, where we have the simple question. It's an expert judgment, but we also have an elaborated version that utilizes norm-based assessments. I go straight now to the next one. I will not go into more details here. If you are interested, join the breakout. So here you see one of the case studies that we have tested. That is the oxide perovskite case study from the automotive catalyst. You see here the results. So from the tier 0, we can learn it's within the scope of the early warning system because indeed it's novel. Yeah, it consists of particles. It's nano-enabled according to the ISO definition, namely it has a nanostructure. And from the category, we learn it is an automotive catalyst. So we should compare it to other more conventional catalysts. So here you see then also the outcome from the simple tier 1, that is the expert judgment. And from the expert judgment, we would enter the early warning system via the hazard first route. And from the hazard question, you see the outcome in the end is red. So namely, we have concerns for this type of material for the following reason. We expect a higher on enhanced reactivity is multi-component. Also from the exposure, you see it's red. So we have concerns here, mainly from the occupational exposure side, but also from the assumed tonnage. From the sustainability assessment, it's an interesting case as we address 2 sustainable development goals, namely the 11, the air quality, which is expected to be improved, while the natural resources would be reduced. And then from the legislation, we don't have any concerns. And that's it. If you are interested, join the breakouts. Thank you.
Thank you very much.
I will skip that.
Thank you, Andrea. So now the fun is on your side. You have to make a decisive decision, selecting the breakout room you want to go in. And these breakout rooms are labeled according to the keywords from the pitch presentations. Then welcome back, everyone. So we're sitting here for a few more minutes just to give you a brief outlook on what has happened and what the future perspective will hold. Wrong way. Oh my God, completely wrong way. Oh, here we are. So just to make you aware of something which was mentioned already by Andrea, we are in contact with the OECD on our early warning system, and in conjunction with other EU project and Sunshine and Sunrise, we are conducting a workshop with the working party of manufactured nanomaterials and the steering group of advanced materials. And we will discuss our early warning system and the Sunshine pre-screening methodology. The date for this is 1st of April. It's an online event. So if you're interested, save the date. We will send you an invite. Yeah, we have you in the list. We will send you an invite once the announcement of invitation comes around. Then future work, of course, is still pending. So we will do some NAM integration into our SSIA. We will also provide a guidance document on our SSIA. And essentially discuss this together with our sister projects, Diagonal and Sunshine, which we had actually very close contact with during the entire project. That was really delightful to see how the 3 different projects interacted and to some degree also provide synergetic effects. And finally, of course, we still work on the high throughput screening omics data sets, which are really promising in terms of AOP anchoring of our materials. There is still some work going on that will be after the project ends, but we are determined to continue working on this route. Then if you want to see more from our side, you can see us at the CETAC meeting in Vienna in May 2025. Also, you can see us at the Association of Inhalation Toxicology Conference coming up in June in the UK. And then essentially, we are, of course, very open for collaboration. So many of us, of course, are going into new projects, but even though I think the willingness to interact and to provide the knowledge we gained as much as possible to others in the community is something we were always talking about, and we are determined to continue to do even after end of life of the project. So please don't hesitate to contact us if you're interested, and we would be more than happy to get some feedback and connections and interactions. Please feel free to contact us anytime. So with this, I would officially close the meeting. But of course, if some of you want to hang around, I will hang around. Maybe some others from Harmless will hang around so we can chat a little bit more. But everyone else who wants to leave, thanks for joining. It was a great pleasure having you here. We had hopefully good interaction in breakout rooms. I was not there, so I cannot tell, but I'm sure it was fruitful. So thank you again. Have a nice afternoon and hopefully see you sometime soon, somewhere in real world engagement. Bye-bye, everyone.